Okay, so I am William Jalby. I'm from University of Versailles in Quentin, and the title is a bit explicit, but I want also to mention that it's not only my work, it's a whole team. So you have a list of people who have really contributed. The second thing, I want really to have some deep and sincere acknowledgements to Altair, which gave us access to their code, and also AWS, Megware, Atos Eviden, and Calmip, which each of them provided us machine time so we can really perform some experiments. So, whoops, I'm stuck. I don't move. I have a problem. Ooh. Sure. Okay, whoops, I moved too fast, sorry. What are our objectives in this talk? So the first goal is we want to analyze and look at what the compiler is producing and the compiler options, what is the impact, okay, on performance. That's the primary goal, but we are not doing it just for the sake of looking at what the compiler is producing. Our ultimate goal is to optimize application performance. So we'll make sure that we can go along this path. So the first things we would like to identify strengths and weaknesses of various compilers and compiler options. Then second thing, which is also interesting, is try to leverage optimization between compilers. For example, if one compiler vectorized a loop, the other one didn't, can we move that vectorization property from one to another one? Third study, which is a bit related to compiler output, is the ISA, and essentially the vector length, but also the ISA. Okay, many machines have produced many different instruction set architecture and want to see the impact. And also all of this methodology, we want to develop it and not only to validate it on simple mini apps, but we want to extend it and to test it on real industrial strength codes. Okay, so it will be the talk overview. We'll present methodology, essentially some key features of Macao WenView and also QAS, quality as a service. We'll make a detail. Then we'll get on Miniapp results, then LAMMPS, which is a well-known molecular dynamics code, and then OpenRadioss, which is a car crash code, and then we'll jump to some conclusion. So the methodology. So what is the standard case, right? You try out compiler A with option 1, you try also another compiler B with option 2, and finally you say, hey, okay, the timing are better with compiler A with options 1, and you stop there. And I think it's an easy but superficial conclusion, which is much more complex. You need to go into more detail, look at the function level, look at the loop level, because the main issue, compiler A can outperform compiler B for a given function, but the situation could be exactly the inverse for another function. There could be compensation between various functions. So as I said, performance analysis, you have to go all the way down to functions, even loops. Okay, now, very often the overall timing will be a bit spread. You will have a flat profile, meaning every function will contribute a few percent to the total execution time, and then you have to perform that analysis. You have to automate it because there are too many functions and loops involved. So therefore, we'll always systematically perform the timings at tree level, the whole app, function level, and loop level. And I will make presentation, essentially whole app and function level. We'll have to look at the output of a compiler, which is the assembly code. And for that, we'll rely on Macao WenView, which is capable of performing various ASM analysis. Essentially, we'll be not only statically using it, but we'll be using simplified simulator to get a feeling of how well or how good is the performance of a given code. A small difficulty we have at some point to have, for example, for a given source code, you can have several variants. So you need to be capable of matching all of these variants back to the source code, but that's okay. So we'll focus essentially on loops, okay, in whatever they are, innermost, in between, or outermost. So we'll use a module which is inside Macao, which is CQA, Code Quality Analysis. We'll look at various things and we'll come into details, but essentially We look at how well the functional units are used, vectorization, use of instruction set, whether vectorization has not been able to be triggered because there were some roadblocks, data access. So we'll perform typically two types of analysis, static and dynamic. Just I want to have an important warning. Since we are looking at the ASM, at the assembly code, we are not only getting the failures of a compiler, but also the quality of the source code. So if the source code is pretty bad, then we'll capture that. Okay, so the performance issues, roughly speaking, we'll classify them into 5 main categories. First, what we call loop computations, essentially computational organization, whether you are using fuse, multiply, add, square roots, divide. Then second, control flow, branches, core, multiple loop level, and so on. Data access, okay, stride, indirect access, pill fill will be the main thing. Vectorization roadblock, okay, by the way, some issues can belong to several categories. For example, vectorization roadblock, if we detect non-unit stride data access, it will be a vectorization roadblock. And sometimes the loop has been vectorized, but the vectorization is a bit inefficient. For example, you are on a 512 bits machine and you are just using 128-bit machines. And here you have an example, okay, of typical analysis, right? So on the right, sorry, you can see penalty score. What does it mean? Essentially, we are detecting drawbacks or failures of a compiler, but we are also associating what we call an estimate of a cost to fix the issue. This is a bit arbitrary, but it tries to a bit identify, and we know also how much points we are attributing, so we can see the exact breakdown. Now I want to show you some typical one-view Macao output. So these are the global metrics. You will see very often that stuff. So average active time. So we are summing over all threads the active time divided by thread count. Ideal, that's the total execution time. The second point, which is very important, is the activity ratio. Okay, sum over threads divided by the sum of wall time. Again, what you are hoping, and you have hit here, activity ratio, not so good. It's 90%. Ideally, we should be at 100%, but 90 is not too bad. Okay, average active number of threads, it's typically the number of threads which are simultaneously active, right? And the affinity stability is just to measure if some threads are migrating a lot between physical cores. All of these numbers that I'm showing there, they are related to the OpenRadioss Torus code on the Torus dataset, and we are using GFORTRAN -03 on a Graviton3, which has 96 cores. So you can see that 86 threads active among 96, not too bad. So it corresponds to a 90% activity ratio. Then the second group of metrics that we are computing, in fact, we are trying to do what-if scenarios. So we are measuring a few things and we say, there are some drawbacks in this code. For example, perfect flow complexity. What does it mean? It means that there are many branches. What would happen if the code was ideally cleaned up? So no more branches or cores. And then you can see 105, 5% gain. Perfect OpenMP plus MPIP threads, similar things. Let's assume that everything has been cleaned up, so there is 0 time spent in perfect OpenMP plus MPIP threads. What is the performance gain? So again, you will gain little. Now, I am the third line, I am adding load distribution, so making sure that there is an equal share load balance between all of the cores. There, the performance gain is a bit better. You could hope for 119, almost 20%, right? So these are two metrics which are important. Then you have also metrics related to vectorization, which are quite important. Floating point vectorization and full vectorization. Fully vectorized, we try to assume what would happen if both the arithmetic and the load store were fully vectorized. Okay, now what is QAS? QAS is, we could consider it as a simple extension on the top of one view. Essentially, Macao 1U is focusing on what? Single compiler option, single machine. Okay, everything is unique. What are we doing with QAS? We are trying to open the scope. We are trying to go across multiple compiler options. We can go all the way also to multiple compiler and also multiple systems and try to automate that. So to some extent, it's really exploring application system performance. And again, we want to perform application performance optimization. What are the key characteristics? We want to automate as much as possible. So we are running and launching automatically all of the runs across different compiler options, different compilers, and even different systems. So here you have a list of the key parameter space that we are pursuing, right? We are also looking at the number of codes and core mappings, and we are also looking at some software stack parameters in general, so such as, for example, the core mapping and so on. So we try to do the uniform exploration because we want to perform comparison. The essence or all of these runs is to make comparison and try to detect. It's by comparing that we'll detect strength or weaknesses. We have added also reliability. We want to make sure that we are comparing reliable numbers for that. So we have some repetition mechanism, and then we have a detailed level of comparison. So the two level of optimization that we have, something which is standard and which will be a typical output. It's automatic, will provide the best compiler switches that we detected, and then we'll provide some recommendation for manual optimization. And I give you here a website where you could get plenty of information. Okay, let's look at Miniapp results. So what are the Miniapps that we have been using? So we have been taking Miniapps from the Exascale project, and essentially we have been looking at 6. Why did we pick up these 6 Miniapps? Because they are quite different in terms of behavior. I would say half of them are memory bound, half of them are more compute bound, more CPU bound, and so on. Okay, so here you have a list, and again, you have a link where you can find all of the details. The big advantage of these mini apps is they are simple enough. The big drawback is they have only a few loops, so it's, I will say, quite easy to optimize to some extent. Okay, now let's look at what we have been doing. So we have been running on a Graviton3, 64 cores. Okay, what do we have? ORIG and GCC. So ORIG is a default, so it means every mini apps comes with this original compiler, essentially directly linked up for the G3 runs. It's ACFL, okay, the ARM compiler. And we have been also looking GCC, and for both of them, we use the default compiler options. And normally we expect that these compiler default options are quite good because these mini apps, they have more or less being beaten to death to get the best performance. As we'll see, it's not easy. Then we have been exploring only 6 compiler options on ARM Clang and 6 on GCC. We group them into 3 groups, some O2, O3, and OFAST, very similar, right? So you can see, and some of them we are forcing no vectorization to see the impact of vectorization. As I was mentioning, it's also a bit the important thing to be done. Okay, so let's look at the results. You will see plenty of tables like that. So let me just look at it a bit more in detail. Okay, so what are we doing there? We are looking at timing ratios, okay? So for each cell, for example, you look at ORIG AMG, the first cell that I'm pointing to with my laser pointer, you see the value 101. What does it mean? I took the timing for the original compiler, right, with original compiler settings, and I divided by the best timing I found for all of the compiler and all of the compiler choices. So it means here that ORIG is 1% slower than the best we could find, okay? And in fact, we have also the clear definition here. So all of the cells which are in green means that we are under 1% far from the optimum, right? Okay. When you look at the yellow cell, we are between 1 and 5%. And when you are in red, we are beyond 5%. Okay, so this is the typical, and you will see many of this, let's say, of this table. So let's look. So you have here the various compiler and compiler options, okay, and the 6 mini apps. Let's analyze it a bit more. So if you look carefully, let's look at the first line, okay? The original compiler options are not always the best choice. For AMG, it's okay. For Cloverleaf, we are a bit over 1.01, but you could say. And Mini QMC, that's good. WebKey, that's acceptable. But you can see that on CoMD, I'm losing 10%, and HECMK, boom, I am completely over. So the original compiler options are not necessarily the best choice, although they have been heavily tested. Now, if I look and I would say, okay, the part, this rectangle here that I'm describing, it's ARM Clang, and here it's GCC. Okay, I would be happy if one of them were more or less uniformly green, okay, and the other one uniformly yellow or red. Tough luck. You can see that sometimes it's GCC which is winning, and sometimes it's ARM Clang. So there is no silver bullet in terms of compiler, right? Okay, you can also say, well, but it's a bit exaggerating. For half of the mini apps, if I look column-wise, let's look at AMG, you could say, wow, the performance is varying between 1 and 103, so compiler options and compiler have limited impact. Cloverleaf is a bit the same thing, and Mini QMC also. Yes, you have half of the mini apps, not a big change. And you can see, by the way, for these 3 mini apps, in fact, the reference, the ORIG was quite good. For the other app, CoMD, HACC, and CryptKey, wow, the situation is fairly different. You can see that some of the performance gains are quite substantial and they are worth being investigating. For example, for HECMK, it's very interesting to see that there were 2 GCC compiler options which really stand out and were capable of outperforming the rest, right? And you can see that the GCC reference was also the good one. Okay, let's look now, because you could say mini apps, well, it's a bit artificial. Let's look at LAMMPS results. What is LAMMPS? Okay, it's classical molecular dynamics. This text is directly extracted from the website. So it's a well-known molecular dynamics code, okay, focusing on materials modeling. Which is nice is that it has been used on single processors, message passing techniques, and so on. So it has been run on many machines, many CPU and GPU. So that's very good. Okay, now, which is interesting, you have a standard reference code, and as you will see, there is a specially tuned x86 version, which provides some very different behavior. Now, let's look here. You can see that we have been using, and I'm giving details there. You have 6 versions of ARM Clang. Okay, 1, 2, 1 is missing, ARM Clang 3, because it failed. Okay, and you have GCC, you have a 6th version. Okay, and you can see that we are again running on a Graviton3, 64 cores. Okay, and we are using various things. So Neoverse V1, you have all of the details of the flags. So you have a total execution time, and also I'm always using the same metric. I'm looking at what is the best choice. And you could say, well, globally, ARM Clang is really the best choice, right? ARM Clang 3 is failing, but except ARM Clang 5, and to some extent you could say, yeah, but it's normal. You force no vectorization. So it's why you are losing a bit, but not that much, which is kind of interesting. And even O2, it's interesting to see that if you compare this first line, this first column versus this column, well, they are almost identical. And here you have O2 versus O3. So you could say, what is the interest there? So you could say GCC is really lagging behind. And it's clear. And you can see, here there is a clear winner, ARM Clang. When I look at all of the characteristics, the activity ratio, you can see it's quite high. So all of the cores are active on the 64 cores are active. So the number of right threads, the affinity stability. So parallelism is perfect. Good. Now let's look, and as I said before, go down to the function level. And if you could see before, you could say before, I don't want to see the details, right? You would be wrong, because when you go down to the function level, you could see that, exactly the same logic, right? Everything you see, you have a various main functions there, and you have arm-clang, the various compilers, and the various compiler options. And you could see, yes, there are a lot of green cells on arm-clang. Great, but there are two lines on which arm-clang is failing, and GCC is much better. So it would be interesting to look at what were the compiling choices made by GCC and to piggyback or to forward them, so in such a way that arm-clang could use them, right? So that's a first interesting case. Now let's move at something a bit more complex. Pay attention, we are moving now to an x86 machines. It's a Granite Rapids 256 cores. And there we look at two things: standard LAMMPS package, then there is an x86 fully optimized LAMMPS package. The best, again, is the same thing, it's the best timing, which is what is standing out, is original default. It's essentially the ICX compiler. The number there, it's the compiler options. I am not reporting the details. Essentially there we are sweeping across 16 different compiler options, but which is very interesting is to see that there are these two best. What does it mean there? It means there that the standard LAMMPS package 2 is 2 times slower than these two codes. And what happens, which is more interesting, is that the compiler is capable of leveraging the x86 optimization, ICX, but not GCC. So you can see that what has been happening is that, yes, the code has been optimized for x86. And you could say if it's optimized for x86, all of x86 compilers should be able to leverage the optimization. Wrong. Okay, a special effort was made and ICX was capable of really leveraging. And if you want to go to the details, they have exactly the same numbers on the top. And if I look, what is the big difference? You could see that the perfect flow complexity is fairly high on the standard LAMMPS package. So the optimized version has been able to simplify it. But which is more important is vectorization. Vectorization, here you can see that there is a large potential gain for vectorization between 363 and all the way to 441. When you have such large gains for vectorization, it means that vectorization originally was quite weak. And here you could see that, there's only 1.1 benefit for vectorization. What does that mean? It means that the ICX compiler was fully capable of vectorizing the loop perfectly. Okay, and that's an interesting feature. So it means it's not because code has been optimized. You have to make sure that it has been optimized and has been able to be really leveraged by the compiler. To some extent, there the lesson is quite simple. You could take all of the loops which have been vectorized by ICX and propagate all of using OpenMP SIMD directives and propagate that on all of the loops. Now let's look at OpenRadioss. Okay, OpenRadioss, it's the open source version of Altair. So you have here the open source version, okay, and the commercial version. What is the open source version? The good advantage, it's really an up-to-date version. To some extent, it's an exploration vehicle, and they use it for testing. If you look at the commercial version, what you get more is professional support, plus some data sets, and so on, which are very important. Models for dummies and barriers, which are quite important. Okay, when we look at this typical industrial code, you have to use realistic data sets. So I've been using Torus, which is a standard car, but 10 million elements. The reference is 1.7 gigabytes. We have been parallelizing for a G4 Graviton3 with 96 MPI ranks. So it increased to 17 gigabytes, and the code is in Fortran and combines MPI plus OpenMP. There is an excellent MPI scaling, and the OpenMP parallelism is a bit more limited. So typically we'll be using in our test either 96 MPI ranks or 48 MPI ranks, each with 2 OpenMP threads per rank. We have to be careful because it's an explicit method, so numerical accuracy has to be taken seriously, and also reproducibility. So we have to use very small time step. Now we have also a difficult issue because the execution time, you need to make it run so long that the crash occurs. It's not like in some CFD code where you have some initialization, then the stuff will be cycling around and it will be a steady behavior there. There is not a really steady behavior because when you send the car on a war, okay, you have some start, some deformation, some pieces are breaking down and so on. So the Taurus run on Neoverse V2, 96 cores, fully parallel, takes over 2 hours. The good point is that it gives you something which is reliable in terms of measurements because it's so long. First, we look at vectorization. First, you have two things to look here. So you have here the loop ID, the coverage, and you see that it's one of the main difficulty is the hottest loop is just 5% coverage, okay? So which means that it's really a flat profile, and then you go down to 3%, most of the loops are under 1%. So what does it mean? It means it's a bit depressing because if a loop is under 1% coverage, what does it mean? Let's imagine that you double the performance of that loop. Well, the overall performance gain on the whole application will be just 0.5%. We'll have a hard time to notice it. So vectorization is not that great. Okay, 48%, the vector length use versus here it's on a G4, it's 128-bit. We are using not fully entirely the whole instruction set. On some of them, it's quite good on this loop. For example, you reach 92% with a very good length use. So, but you see the flavor. So vectorization is okay, but still resisting. Now let's look here. We have been looking GNU versus ACFL. We look first at the total time. And we have O2, O3, O3, no SVE2. SVE2 is the typical instruction set of G4. And O3, no SVE. What this means? It means we force it back to something prior to Graviton3, okay, to Neoverse, okay, before Neoverse, right? So it's interesting if you look at the numbers, you could say where there is some performance variations, but not that much, right, between O2 and O3 no SV. On ACFL, well, there is not much a big difference. You could see that, which is still more important. You could say GNU is a bit winning, okay? Well, although we can argue, right? The best here it's 7.41, and the best here is 792. You could say nothing much. The activity ratio is quite good on all of them, so parallelism is quite good. Now let's look in more details what is the real winner, right? So, okay, the worst is O2, which is a bit expected. Okay, hey, finally, what is the best? And it's a bit surprising. It's no SVE. So it means you are running on a machine which have a specific instruction set, preventing the compiler from using its specific instruction set gives you the better performance. That's a bit annoying, right? Okay, now let's look at ACFL. Okay, for ACFL, it's a bit more balanced, right? You could see that here, no SVE, so not fully using the G4 capabilities, kills you a bit, you are at 826. And then all of the three here, they are very close to each other. So finally, there is not a big difference. And you could conclude, yeah, all of this talk is useless, right? If I look at real industrial code, compiler option has no effect. Let's look at a bit more in details. Okay, here it's a quick summary, right? About what is happening, O2 is worse, okay, and so on. And GFORTRAN is better than ACFL, on average 6%. for both compilers and options, a large amount of time is spent in loops. Now let's look at more details. Let's look at the function level. At the function level here, I have 4 options. I'm looking at GFORTRAN and I'm looking at the time. Okay, so here, lower is better, right? You can see that, here, normally if everything was equal, okay, the four bars should be equal. And you can see that some of them, no, that's not clearly true. You could say, if I look at the first 2, you could say, I understand. Okay, the first one, GNU minus O2 is not good. Well, it's not always the case. Sometimes GNU O2 is quite good. Okay, and you could see that it's kind of interesting. There is not a uniform behavior. For example, you could see that here, no SVE. Wow, on this particular function, particular loops, is really much better. So it's much better to look at what's happening there, right? So every compiler options as a general conclusion is sometime losing, winning at other times. So again, I was saying that O2 is always winning, but if you look into more details, in this case, it's winning. Okay, let's look at some more detailed analysis. If we want to look at it, if we look at the IC Open 70 functions, essentially the difference comes from a loop, which is stupidly computing, conditionally setting arrays values to 0. And the no SVE option, so saying don't use the fancy instruction set, takes 25 seconds. And wow, if you let the compiler use the SV version, 90 seconds. So almost a ratio of 3, and the timings are large enough so we can really rely on it. So there are multiple factors, but it's kind of interesting to see the big gap. The other one on IC7, one of the loop is vectorized in neon only. Neon is the predecessor of the SV instruction set, and it's better than SVE. So might be a bug or in the CUS model used by the compiler, but still we are looking at it. Now let's look at ACFL. Again, the same thing. So here you can see that, wow, but no SVE is clearly losing, right? So now no O3 no SVE is a compiler option with a largest impact. Sometimes it's winning, it's not always losing. You have to be a bit cautious. If you look, for example, this is the yellow, okay, which is the rightmost bar. So wow, on the heaviest loop, it's really winning, right? Okay, and while here it's losing. So you have to be a bit cautious, again, to take into account the differences in terms of behavior. Now let's look and let's put everything together. So here what I'm doing, I am putting the best 2 of ACFL, okay, ACFL O3 and ACFL no SVE, and GNU O3 versus O3 no SVE. And I'm taking again the same loops of the same functions, and I'm looking at the behavior, right? So here I draw some equality lines, okay, some, dark lines, black lines, and under it's ACFL, which is faster when you look at the red curve, and on the top above it, GFORTRAN is faster. So if I look at this loop here, where I see a big peak, okay, and you can see that here there is a big difference in the histogram bar. So GFORTRAN is clearly much faster for this function, CZ fork 3, right? Okay, while on another loop, you could say that, it's ACFL, which is faster. And here it's much more interesting because, okay, the difference can start jumping and spreading when you combine both compilers and both the compiler options. If you want to look at globally, and I will make a quick summary, if you want to look at fine-tuning compiler options, you could shoot for 5% performance gain on the whole application, which is quite important. Now, if you want to play fine-tuning across compiler and compiler options, it can go all the way up to 10%, right? Now, it's easily said. It's the second point is much tougher to reach really, because you need to be able to carry over some of the optimization from the compiler to another compiler. So you need to be using compiler pragmas at the loop or the function level. Now, what is the future work that we plan to keep on going? So we plan to analyze more compiler options, fastmass, FNRO. The big important point is to be able to automate the backport, okay, from one compiler to the other one. Pragma insertion, if, for example, if a compiler has been able to vectorize a loop, you could say, and the other compiler didn't. Okay, I will use and I will try to insert an OpenMP SIMD directives to force vectorization, right? We could also interact with compiler developers to refine and improve cost models because some of them are clearly wrong, and application developers also to be able to use this technology and not to stick to a single compiler. Now, what you look at the conclusion, you could say, well, what did we see? Non-uniform behavior across compiler options, non-uniform behavior between compilers across subroutines and loops. Good. Non-uniform means non-negligible performance differences. But you could say, hey, all of that I knew, right? Okay, nobody's surprised. Now, what does this talk brings to you? A real evaluation, a quantitative evaluation. And the good thing is Macao and QAS provides you not only a qualitative statement as, yes, this compiler is better, but more precisely how much you're gaining and also why. Because it's very important to know, okay, good, on this loop I am gaining 10%. Okay, but why? Is it because it's vectorized or is it because you restricted your vectorization length? For example, it's interesting to see that at some point I was getting a better performance because I was using a scalar performance. Okay, this is very important. These 2 points, the quantitative estimation and the explanation of performance differences. This opens the door to backport. And thanks a lot for listening. And okay, I am done and I am welcoming questions. Hello.
Yeah, thank you, William.
Alors, just a final point that I want to stress out, all of the data that I was showing, you will see that you will be able to access it. There is a website where you could access in details all of the data that I was showing. There will be a copy of the slides which will be distributed by Bernd, and you can access all of the data.
Okay. Yeah, someone asked already about it, and so as in the past for the pop webinars, the recording and the slide will show up in the blog of the pop website, but also on the YouTube channel, and all registered users get a notification when it's ready, likely tomorrow. Okay, are there any slides about the talk itself?
Any slides, you mean any questions?
Yeah, sorry, any question? So far, I don't see anything in the chat. So you're welcome to open your mic and ask directly if you want. I don't see any hands raising. Yeah, here. From Mr. Lanukarna from Shinika. Aggressive compiler options may lead to different results. Is this validation process part of a machinery?
Alors, no, I think we wanted to stick because we could push further, right, in the compiler flags. If you look, for example, at spec, you could see that for the best numbers, they are pushing to death the optimization. We wanted to stay with, I would say, standard compiler flags. At the best, we were using between 10 and 16 compiler flags. We are not pushing for two specific compiler flags. What we found out also is that on large scale application, very specific compiler flags in general do not pay off that much because they could only target a few key routines. but we want to stay with, I would say, standard compiler flags. Okay, and which for us was very amazing. If I come back, let me come back. Can I? Yeah, even which was impressive for us, even with this 4 compiler options, which are very standard, to observe that there was so much a difference. We're amazed, and even on that one, for example, when I look at where is it? Yeah, this one, for example. Okay, we were a bit surprised that we were not even very aggressive. 6 compiler options for both compilers, and already you have a large amount of difference. But it's clear that we could have a few more. I mentioned in my conclusion that we will look, for example, at fast math. We look also at including perhaps also some libraries, because for some codes they are quite sensitive to the library. Okay, so we'll add 1 or 2 more compiler options, but not much more. We don't want to enter the game of systematically searching what is the best compiler settings. We don't want to end as in some spec codes where you have half a page of compiler options to get the performance, the best performance.
Yeah. But I think it's touching, and the question is touching an interesting topic. Yeah. So how to ensure that the results are really the same, especially if, say, it outputs large blocks of numbers, yeah, where a slight numerical variation, whatever, to some epsilon might be fine or not. So if I guess handling that in general will be difficult. So I guess the different codes, which is a good thing anyway, should have some sort of validation step at the end, whether the reduced results are still fine.
You're fully right. In fact, in QAS, for some codes which have such a numerical check, we included the option of being able to check that the compiler didn't change, didn't mess up.
Okay, we have more question now from Francesco or Nano. Hi, thanks for the presentation. Do you expect the differences between compilers to vanish as compilers keeps improving and language follows stricter standard rules?
No, I don't expect, because it's difficult. The game is extremely difficult. There is the cost, which is kind of the cost model, which is very difficult to tune. And don't forget also that the compiler guys, they are very constrained. So compilation time has to remain under some very tough constraints. So I don't expect to get better. Even I would say I expect it to even a bit worse. And which is interesting is because we have been carrying these tests among Sapphire Rapids, Skylake, Graviton3, Graviton4, and so on, especially with the Miniapps. And it's still all over the places. We observe exactly the same thing. So I would say compiler task is quite difficult, and they don't have so much time to resolve the issues.
Okay, then another question from Antoine Morin. What about applying meta-heuristic to flags, compilers exploration, or even going more crazy, give it to the control to some sort of artificial intelligence?
Well, I would say, look, I want to have something simple. Here I am doing an exhaustive search, boom, and I am taking the best. And I don't want to think a bit more. And then doing the exhaustive search, it's more limited, but I can guarantee you the results, right? So AI could give some perhaps extra benefit, but it's not so easy to exactly drive. And you have really a large bunch of compiler options, which are a bit difficult to manage. There is one compiler option that we didn't include and we could discuss about it. We didn't include PGO, Profile Guided Optimization. And we know, because we did a lot of experiments on spec or analyzing the results obtained on spec, and we know that it's a quite good optimization, PGO, except that it needs two runs, okay? And the problem is that it's very specific to a data set, which is a bit bothering me. But again, I would say I want to have something which is quick, reliable. Yes, I can go beyond what we are getting, but I'm already happy to get such a performance level and with limited amount of effort. Sure, we can do better, but sure, it will be more expensive. But if you have deep pockets, go ahead.
Okay, another question from Augustin Digom. For HackMK, what was the cause for such performance advantage for GCC in the end? Specific pragmas for driving GCC?
Yeah, specific.
Vectorizer managing to work on it while others failed.
Yeah, the other ones, they didn't get, it was a library issues, and they were capable of fully taking advantage of it. In fact, if you look at the same numbers obtained on Sapphire Rapids, you could see that the Intel compiler is picking up the right optimization. It's arm clang, which is quite bad.
Yeah, and then Piero again from Shinika, the presentation shows some relevant performance metrics. If I'm not wrong, will this set of performance metrics added to the set of pop metrics in some way? I guess he's referring to the vectorization metrics, and yeah, they are discussed in the overall POP methodology work package, how they can be generally added and supported. But William, you're basically deeper into the topic than me and can say something about it.
Yeah, the problem with this metrics is to get a full agreement, okay? And in POP, I would say we are more focusing on the parallelism issue, okay? So here, vectorization is more related to the core issues, okay? Because you could say also that there are some other metrics which might be interesting is the data access performance, the fact that there are non-unit sprite access. There are many metrics. What I would say is that POP is really trying to focus on parallelism issues, MPI, OpenMP, and even now with GPUs. So we have already plenty of things on the plate with these three metrics.
Yeah, I think we can easily add it, and they kind of how you say that, they add, yeah, like you start with one, and then if POP finds out the issue is more on the single core performance level, these additional metrics help you. But I think directly integrating, if I remember the discussion right, because the rest of the model thinks about inefficiencies which go from 0 to 1. And here you have other metrics which do not follow this efficiency style. Yeah. And this is why they are harder to integrate. Okay, so final call for new questions. Yeah, I think that's what it is. So thanks again, William, for this really interesting talk, highlighting again that, yeah, especially when it comes to performance, some basic guidelines can be told, but in the end, if you have a specific case, it always comes down to measure and exploration and find the best result, and guessing is not always the best option. Like measuring is always the best one.
I fully agree with Bernd, and they have Ulish has been developing very good tools for measuring them. So, and I think it's important. Measurements, it's the ultimate judge.
Yeah.
So yeah, that's the end of the day. And feel free to send me questions by mail and so on. I will be very happy to answer.
Okay, so thanks again, William, for the recording, and thanks for everyone joining.
Okay, thanks. Bye. So I will stop sharing.